Hey guys, what's up? So really sorry that I couldn't upload the video these days because I was very busy with my works and all. So let's start without any wasting any time. So today we'll start with the second application of op amp in the negative feedback, and this is inverting amplifier. Last class we have discussed. Last class we have discussed about non-inverting amplifier, and today we'll be discussing inverting amplifier and other applications of op amp in the negative feedback. And let us see, and we will find what is input resistance, what is output resistance, what is the closed loop bandwidth and stuff like that. Okay, now just remember, right now my op amp is ideal. We will discuss what the imperfect condition of op amp after some days. Once we are done with all the ideal applications of op amp, then we will discuss imperfect condition. So for the time being, see, the input current to the op amp is again 0 ampere 0 ampere. Now the current that is flowing over here will again flow will be the current that is flowing over here. So you can say that the current through R1 and R3 is same, RF is same. So R1 and RF are in series, and that's why you can let us call this node as node A and this node as node B. And according to virtual ground, the voltage will be same. So VA is equal to VB. Now since VB is equal to 0, we can say that VA is also 0 from this logic. Yes sir. Now what is VA? I told you this logic, right, in the last class. If two resistors are connected in series, this point having voltage VB, this point having voltage VA, and these are R1 and R2, you can find the voltage at this node, which will be called VX. I told you, and the same logic I have applied. Now if you put this entire part of this is equal to V and this is equal to 0 from here, and if you solve this one for a relation between V dot and Vi, what you get is this much. Now just hold on over here. See, what is the entire meaning of this inverting amplifier? See, V0 and Vi are in out of phase by 180 degree, and this is the amplification factor that Vi is getting multiplied with to get the V0. Always RF is greater than R1. Just remember this thing, this will be asked in interviews. Always RF is greater than R1. Okay, now the input resistance. I told you two logics. Either you will find it is the resistance between input node and ground. One logic is this, and another logic is it's the input resistance is equals to input voltage by input current. Now what will be the input voltage over here? Sorry, Vi. Okay, we will see input resistance from this point. Now what is this input resistance? This is Ri here. This is my plant, this is the entire feedback path, so this is Ri here. What is Ri? Input resistance of op amp. Ri is input resistance of op amp, which is never asked. Okay, they will tell you to find the input resistance from this side. If they show the arrow like this, that means it's the input resistance of op amp, and this is equal to 1 to 2 mega ohm. Okay, so I am doing it for the very last time just to clarify. From here on I will just say input resistance. Okay, so this is RIF, which is the input resistance of the entire feedback connected system. So input voltage by input current. Now what is input current? It's very difficult to find out, so we will go for the next logic. I am drawing over here again this circuit. If you can just understand from here, it will be very easy for us. See, and then this is the feedback path. See, it's okay. Now see, if this voltage is ground 0, this voltage is also 0, so can I say that this point is also ground? And what is the node? This is the input node. So what is the resistance that you are seeing between the input node and ground? This is the input node and ground, this is the input node and ground. So this is the resistance that you are seeing between input node and ground. So the input resistance of non-inverting feedback amplifier is R1. Sorry, it's R1. What is output resistance? Take it to be 0 ohm. Okay, how it is, sir? We will discuss it afterward. Again, one more thing. What you are putting as input? Vi. What you are getting as output is V0. So again, it is my op amp is acting as a voltage amplifier again. So it is output voltage by input voltage. So my op amp is acting as output voltage. Voltage amplifier. Now, what we want is our input resistance will be as high as possible. Now in the last class we have discussed Ni is having Ri equals to infinity. You remember that, right? Now we want our input resistance to be high. Why, sir? Because we want to overcome this loading effect. Now sir, what is loading effect? I will tell you over here. Suppose everybody knows this formula, right? Voltage gain is equals to Gm into RL dash. Yes sir, we have seen, everybody has seen this formula. What I want to say is the gain of any amplifier, voltage gain, the gain of any amplifier is proportional to the load resistance of that amplifier. Now suppose this is my first amplifier and this is my second amplifier, and both are connected in cascade. Okay, now see what I want to show. Please understand this. If this is the input resistance and this is the output resistance of R1, so this is Ri1 and this is RL1. Now this is the input resistance Ri2 and this is again the output resistance RL2. Now if I tell you find the voltage gain of first amplifier AV1, what you will tell is, sir, AV1 is equal to Gm into RL dash. Now what is the output resistance of this amplifier, if you see from this side, what you are seeing, this and this resistance are connected in parallel. So RL dash is my RI1 parallel to, sorry, RL1 parallel to RI2, RL1 parallel to RI2. So now understand this. Suppose I am just getting it over here. Suppose, just understand this part. Suppose my RI2 is 1 kilo ohm, okay, and my RL1 is 100 kilo ohms. Now if you connect both this in parallel, the output resistance will be somewhere into 0.9 kilo ohm. Yes sir, because in parallel connection the lower value dominates. Okay, now see what would have been my output. Suppose GM is equals to 1 Siemens. Okay, so if GM is equal to 1 Siemens and suppose RI2 was not there, okay, this amplifier was not there, then what would have been the load resistance? RL1. Okay, so GM is equal to 1 Siemens equals to 100 kilo ohms. Okay, so this would have been giving a gain of 100. Now if this is again coming into the picture, this RI2, then what will be the gain? So the gain will be 1 into 0.9. This is 0.9. Now you see that the gain which could have been 100, now it has been reduced to just 0.9. So this is the effect. How it comes into picture? Because sir, RI2 is having a very low value. The input resistance of the second amplifier is very low compared to the load resistance of the first amplifier. Now second case is, suppose RI2 was 110 kilo ohm, RL1 was 100 kilo ohm, then what would have been the resultant? Somewhere around 100 kilo ohm, somewhere around, obviously the lower one dominate. Now what is the gain of the amplifier? Again GM into RL, this will be around 100. Now without this second amplifier, the output gain was 100, voltage gain was 100. With this second amplifier having input resistance as 1 kilo ohm, what we are getting, our gain is as 0.9. Now with this second amplifier having input resistance of 110 kilo ohm, what you are seeing is your gain is equivalent to 100. Now you can understand, right, which is better for you? Yes sir, my RI2 should be greater than RL1. Now this decrease in the voltage gain due to the input resistance of the second amplifier is called loading effect in our analog circuit. There are various different definitions that you will be reading for loading effect. What I know is this much only: the decrease in the voltage gain of the amplifier due to the input impedance, low input impedance of the second amplifier is called loading effect. Now how can you overcome loading effect? If the input resistance of the amplifier is high, so we are saying that input resistance of the amplifier should always be high. Now this is an issue over here. My input resistance is R1. Now for my input resistance should be high, so I will keep R1 to be high. But sir, I have to get some gain, right? And what is my gain factor of this circuit? RF by R1. So what you will say is, sir, if you are increasing R1, suppose R1 was 1 kilo ohm, okay, and your gain of the circuit is 10. Okay, now if you are increasing R1 to 10 kilo ohm, what should be your RF? 100 kilo ohm. This is also okay. If you increase the RM to 1 mega ohm, okay, you need resistance to be like this only, right? 1 mega ohm, 2 mega ohm, high resistance is 1 mega ohm. So what should be the value of RF? Now RF should be 10 mega ohm. Now there where the issue starts. Okay, what happens is, it's very difficult to get a practical resistor having values as 10 mega ohm, 100 mega ohms. Okay, so what you will do is, you have to overcome this problem, and for this a special circuit is developed, okay, in which for inverting amplifier. Okay, now this is the issue. Yeah, just remember what is the issue of inverting amplifier is, the input resistance of the circuit is sir R1, and if for having high input resistance we have to keep R1 to be high, but if we keep R1 to be high, we have to increase the RF value also, so that my gain is managed. But if you are increasing RF to a very high value, practically this is not feasible, and that's where all the issue begins. Okay, so what we do is, one of the circuit that has been mentioned in Saddle Smith is something like this. It's a bit easy only. देखने में थोड़ा it's like a difficult circuit. This is some kind of circuit they have managed. This circuit is said to be having a very high input resistance. How it happens is, this part of branch also comes in series with this part of the resistance. When you calculate, you can go through Saddle Smith for this question. Okay, you will understand it in a better way over there. So you say that overall the input resistance increases. Now you can understand like this, right? This is ground. Okay, this comes to be ground, and there is some voltage for this, for which this resistance also comes in parallel series with this branch. So you can read over there. So this is one of the circuit that is being used to increase the input resistance of inverting inverting amplifier. Now the next point is, what will be my bandwidth of the inverting amplifier? Simple as that. This is the formula that we will use. ACL into FCL is equal to UGB, where FCL is called the closed loop bandwidth. What is ACL? Sir, ACL is RF by R1. What is RF by R1? It is the closed loop gain of the above circuit. Now moving on to the next circuit. Next circuit for us, for our discussion, is voltage buffer. Now what is buffer? In simple words you can say is V naught is equal to Vi. There is no kind of gain and stuffs in this. You can understand also over here. See, this is Vi, input current is 0, again this input current is 0, so the current through it here is also 0 ampere. Since this Vi, this is Vi, this is also Vi. Now you can see that this part is short circuit. So can I say V naught equals to Vi? Yes sir. So what is my V naught by Vi? This is equals to 1. This happens to be my closed loop gain also. See, this is a closed loop gain, right, circuit. Okay, so this is my closed loop circuit. Okay, now what is the input resistance? So input resistance is the resistance between input node and ground, or it is the resistance is found out by a ratio of input voltage and input current. So Ri is equals to, sir, Vi by 0. So it happens to be infinity, which is very good. Now R naught will be 0 ohms again. Okay, why? Because it is increasing, it is taking as input voltage, and the output is also output voltage. Okay, so overall it is taking as yeah, it is just decreasing the output resistance. Take it for granted. Okay guys, just remember R naught is 0 ohm, and why it is so you will understand. We will be discussing feedback amplifier. Now, so what is the closed loop gain? This is equals to 1. What is bandwidth of closed loop? You can understand like this: ACL and FCL equals to UGB, and then this FCL equals to UGB part kind of thing. Okay, by ACL is 1, so FCL is equal to UGB. Now one you have remembered full power bandwidth. Yeah, we have discussed. So basically there we have taken ACL full power bandwidth, or I have called it to be large signal bandwidth in the basics. So that was a term that was derived for simply a voltage buffer circuit also. Okay, so you can link that part also to here. Okay, now what's the use of this circuit? You will see some of the uses of the circuit. See, many of them if you have doubt, sir, if the gain is nothing, then why the hell we are using this entire circuit? Just to increase the area? No. The advantage of this circuit is something that you will understand when we are discussing in instrumentation amplifier and sample and hold circuits, and you will understand that part. Okay, and similar kind of circuits of a buffer kind of circuit are also seen in case of BJT and also in case of FET. So this is a very important topic. Now I'll discuss a question over here that was asked to me in this year's ISRO interview only. They asked me to draw a frequency response of an open loop op-amp. So what is my frequency response of open loop op-amp? This is my frequency response of open loop op-amp. This is A, this is F. Then the next question they asked me is draw a buffer circuit using op-amp. I have drawn this circuit. Now they ask me, tell me what is the frequency response of this circuit. Okay, so can anybody guess it? What can be the circuit for what can be this our frequency response for this circuit? I'll tell you like this. This will be the same output will be there, but the bandwidth will increase and the gain will decrease. Why, sir? Because we have applied negative feedback in this circuit, and because we have applied negative feedback in this circuit, the gain of the circuit is decreasing, but the bandwidth of the circuit is increasing. Hence you can see that the entire bandwidth has increased and the gain has decreased. For the red one, which is the open loop frequency response, you can see that the bandwidth is less and the gain is more. So this was the question that was asked to me in the interview. And the next question was, why is it so, sir? Because gain bandwidth product is constant we take. Okay, so that is the logic behind this question. Now moving on. So this is voltage buffer. What are the uses? You will understand in the next some sections that we will be discussing over here. Okay, so the next circuit that we are using is